Nous allons écouter Dominique Bourn qui va nous parler de profuncteurs et de cohomologie de groupe.
Okay, good morning to everybody. I am very glad to have the opportunity to contribute to this meeting in honor and in memory of Jean Bénabou. And this is mainly because during many years, he was the only one in France to maintain a weekly seminar in category theory. Every Saturday morning at 10, there was a place at the Institut Henri Poincaré in Paris where I learned many things in that field. And so I am personally very grateful for that to Jean Bénabou. As for the details of the scientific contribution of the mathematician, I should refer to the recent article written by Francis Borseux and published in the Cahier de Topologie, where beside his bibliography, Francis Borseux offered, in my opinion, a very faithful portrait of the man who had a rather complex personality. As for me, one of the major contributions of Jean Bénabou to category theory is certainly the notion of profunctor, introduced in the 70s of the last century, or more exactly, the difficult part of the theory, more exactly, their composition, thought as a kind of generalization of the tensor product of module. In this talk, I should like to show how much this notion is an extremely powerful tool of synthesis. And I shall do this by showing that a special kind of profunctor is underlying any exact sequence of group, and by showing how this observation enlightened some well-known aspect of cohomology theory. So I shall begin by recalling what is a profunctor. Basically, a profunctor between a category C and a category D is a functor from C up times D to set. And then an element of HCD is represented by a virtual arrow relating the object C in D and an object D in D. And now, given any other profunctor between two other categories, the composition of the two profunctors is defined in the following way. The set of virtual arrows between an object C in C and object E in E is given by the set of connected components of the category whose objects are the pair of virtual arrows with a same domain and a same codomain in the category D, and whose morphism is represented by this diagram, namely that this pair is so F determine a map F between D and D prime determine the morphism between this pair and this pair if and only if you have this equality. In other words, you set that the couple phi key F is equivalent to the couple phi F phi key for any F relating D to D prime in D. This gives rise to a B category. This composition gives rise to a B category, and in the sense of Bénabou, which is a generalization of the notion of category. I mean, What is important is that this notion of profunctor keeps a full meaning on both sides of category theory, namely the V categorical one and the internal one. As for me, what did I do? I don't know how to, I don't know what to do.
Le bouton vert.
Le bouton vert, oui, le bouton vert.
En haut.
Là?
Ouais.
Ah, merci. Bon, merci. And so I shall work in this talk in the internal side, but some weeks ago I attended a very good talk by Isar Stuber using the categorical version of the notion of profunctor. So I have to recall how this notion of profunctor can be internalized. It is internalized by defining a profunctor between an internal category X and an internal category Y by the data of an internal discrete bifibration across over the product, namely internal discrete bifibration means a pair of split fibration and a split cofibration, which are related in such a way any map in W can be decomposed in a unique way as a composition of a Cartesian map with respect to psi and a co-Cartesian map with respect to psi. They can internally be composed as soon as the ground category E is exact and admits a co-equalizer of reflexive pair which are universal, which means that they are stable under pullbacks. And the composition mimics the composition of relation, since starting with a pair of composable profunctor, you first take the pullback of the two legs with a common domain, and then you decompose the external pair here through the universal discrete bifibration, and the condition on the category E are exactly the condition where this construction is always possible. A very easy remark is that when X and Y are internal groupoids, split fibration and split cofibration, the two notions coincide. So any profunctor from X to Y gives rise to a profunctor in the opposite direction, and we shall denote it by a phi psi star. So I speak in the introduction of a special kind of profunctor. So I am going little by little to precise what special class of profunctor is dealing with exact sequence. So a profunctor between two groupoids, between two categories is said fully faithful when any of the two legs is fully faithful, and it is said regularly fully faithful when, moreover, the two ground maps of the leg at the level of object are regular epimorphism. The fully faithful profunctor and the regularly fully faithful profunctor are stable under composition. And more spectacularly, given any regularly faithful functor, its opposite between groupoids, its opposite coincides with the inverse in the category of profunctor. And this is rather surprising, and a rather surprising characterization of, in this situation, of the inverse, and of course, it is very useful. And now a last step, I have to add another ingredient, the notion of affine groupoid. An internal groupoid in a category E is just 3 truncated simplicial objects in which every commutative square is a pullback. We denote by GRD E the category of internal groupoid, and by 0 the functor associating to any groupoid is object of object. It is a fibration whose Cartesian map are the fully faithful functor. And actually, it is a very rich fibration, since we have 2 important properties. Any fiber of this fibration is protomodular. That means that it shares many properties of the category of groups, because of internal groups, because the category of internal groups, of course, is one of the fiber of this fibration. It is the fibration number 1. So this any fiber is protomodular, and thus a Mal'Sev category. Accordingly, lies in any fiber an intrinsic notion of affine object, which I recall in a moment. And moreover, when the ground category is exact, and when you have an object with global support, namely such that the terminal map is a regular hypermorphism, the change of base along this terminal map, which relate the category of internal group in E to the fiber above Y, produce an equivalence of category at the level of abelian object. So there is, when E is exact, there is an equivalence of category between the abelian groups in any fiber, and provided that the terminal map is a regular hypermorphism, and the category of abelian group. So you see, this fibration of internal groupoids are very strong structural properties. Now, I am recalling some aspect of what are affine objects in a Mal'Sev category. In a Mal'Sev category, the 2 following conditions are equivalent. The object X is endowed with a unique Mal'Sev operation, namely a ternary operation P satisfying the Mal'Sev property. And this Mal'Sev operation is necessarily associative and commutative. And the second condition, the condition which is equivalent to that, is that the indiscrete equivalence relation on X is centralizing itself. And now when is exact, then to any affine category with global support, so let X be a Mal'Sev, an affine object with global support. Global support means that this is a regular hypermorphism. Mal'Sev means that you have a centralizing double relation on the indiscrete groupoid, and the centralizing relation is constructed from the ternary, from the Mal'Sev operation exactly by the diagram. So you get here above an equivalence relation. Since E exact, you can take the quotient. This determines an object dx, and since here this is a regular hypermorphism, the diagonal give a section, and actually this object is an internal abelian group in E, and which is called the direction of the affine object with global support. This construction is exactly the same as the one associating with any K affine space where K is a field, its associated K vectorial space. And now I am going to precise what are the affine groupoid in the fiber. So given any internal groupoid X, consider the pair of the D0 and D1 of domain and codomain. This is an object in the slice category above X0 cross X0. And as soon as X is an internal groupoid, this object is automatically endowed with an associative Maltsev operation, which is defined on any triple of parallel pair by this definition. And this, of course, at first sight, it is a Maltsev operation, and it is a Maltsev operation on this object in this category. And so now I can produce a characterization of what is an affine groupoid. For an internal groupoid, the following conditions are equivalent. The ternary operation above is commutative. Any group of endomorphism in the groupoid X is commutative. More spectacularly, given any map between two objects X and X prime, the induced group homomorphism from the automorphism of the domain to the automorphism of the codomain given by this formula is the same. It is independent from the map theta. And the fourth condition is that according to the definition in the Maltsev category, the object X is an affine object, since this condition make this a functor, and so this gives you the Maltsev condition inside the fiber. So accordingly, a groupoid X is affine if any of these four conditions is satisfied. And of course, seen as it is not surprising that seen as a groupoid with only one object, an entire group is affine if and only if it is abelian. So, what is? There is something wrong here. So, oh, yes, everything is good. And an important property is that when the category E is Maltsev, any internal groupoid is affine. And so this will be the case for the category of group and any slice category of group above Y. So when E is in exact category, you can, of course, do the previous, and if you have an affine groupoid with global support, that means connected, you can do the previous construction inside the fiber, and so any affine groupoid which is connected determines an internal group in the fiber, which is called the local direction of the groupoid X. And when, moreover, the terminal map of the object is regular epimorphism by the equivalence between the abelian group, this abelian group in the fiber determine an abelian group in E, which I call the direction of the affine groupoid. And for sake of simplicity, I shall define as aspherical a groupoid which is connected and such that the terminal map of the terminal object is a regular epimorphism. Of course, in the set theoretical context, the second condition disappeared because saying that X0 as a global support is saying that X0 is non-empty, and so in the theoretical concept, it is often forgotten. But here, working internally, we need absolutely this notion, and so you have to precise this notion of aspherical groupoid. And for sake of simplicity, given any group G, I should denote by KJ1 the associated structure of groupoid with only one object. Of course, it is an aspherical groupoid, and it is affine if and only if J is abelian. And as expected, the direction of this aspherical affine groupoid is A itself by the very easy construction, where the quotient, the desired quotient, is nothing but the difference of the projection. Of course, the constructions of the direction can be extended to functors between aspherical affine groupoid. And we can characterize fully faithful functor of this kind by the fact that the direction is an isomorphism. And from that, you can absolutely characterize the functor in a fiber, which are isomorphism, by the fact that its direction is an isomorphism. And so, as you see, the direction on an aspherical affine groupoid is a meaningful characteristic index of the groupoid. Now we are in position to get the final precision of the special kind of profunctor dealing with this talk. An internal profunctor between two aspherical affine groupoid is said to be affine when it is regularly fully faithful and when the direction of the two legs are the same. We denote by F prof xy the groupoid of affine profunctors between aspherical affine groupoids. This kind of profunctor is stable under composition, and as I said before, when you have an affine groupoid, its opposite is inverse, and of course it is obviously affine if the phi is itself affine. So when you have a category which is exact with universal coequalizer of reflexive pair, the affine profunctor between affine groupoids determine a sub-B groupoid of the bicategory of profunctor. And this is the key result of what I have in mind. Now I can relate the notion of exact sequence in groups and the notion of affine groupoids. So let Kj be any exact sequential group. Of course, we can produce a factorization from X to out K through the inner automorphism of X, a factorization theta of the canonical action of K on itself. So you can define by this group homomorphism theta decomposition of this map through the kernel of the exact sequence. Once the following morphism of exact sequence, since here, if you decompose GK by surjection and an injection, you determine the inner automorphism of K, and then this map theta determine a factorization from Y to the quotient of out K of the automorphism by the inner automorphism, which is often denoted by out K. It is well known that any morphism of exact sequence which fix K and Y is an isomorphism, and classically X1 phi xk denotes the set of isomorphic classes of extension producing the same factorization psi. Eglenberg and MacLean called abstract kernel any group homomorphism psi between Y, given any group Y and K. They call abstract kernel any group homomorphism between Y and out K, and they characterize those abstract kernel which comes from exact sequence between Y and K by very spectacular algebraic combinatorial calculus called obstruction to extension, and by the vanishing of this obstruction. We, on our side, we are going now to give a categorical characterization of the exact sequence with abstract kernel phi via Profunctor. So for that, we need a bit of notation. Starting with any group K, you have the canonical action that I denote by GK. Actually, it is in the underlying crossed modules, and it determines an internal groupoid in the category of group. I shall denote by act K. This action groupoid is as out K as object of object. The crossed product determined by the action as object of morphism. The first projection is the domain map. The identity map is given by the for any sigma by the couple of sigma and unit of K, and the codomain map is just the composition of the inner automorphism determined by K and sigma. This is an internal groupoid in the category of groups, and obviously the quotient from out K to come out K to out K is nothing but the equalizer of the D0 and D1, and so this represents the P0 of in the category of groupoid of this internal groupoid. And since we are working in the category of group, which is the Mal subcategory, this is an aspherical affine groupoid in the slice category above this object. So it has a direction, and we have to determine it. For that, we need the restriction homomorphism from out K to out ZK. It is well known that any automorphism of K determines an automorphism on the center of K. It vanished on the inner automorphism, so this ZK, so this produces a factorization R, which is an action of out K on out ZK, and this in turn determine a split AP by the crossed product, a split AP above out K, and since ZK is abelian, this is an abelian group above out K, and this is the direction of the of the action groupoid. Now, you have an internal discrete vibration from the undiscrete relation on K and the action groupoid by this pair of map where there is a division map. Of course, the division map is not a group homomorphism, but this couple determines a group homomorphism between K cross K and this group. And now, starting with any exact sequence, we are here in the heart of the association of affine profunctor. So, if you here above you have the vibration that I described before, if you introduce here the homomorphism with kernel K, you get here a factorization between the kernel equivalence relation and this, because of course the division map applied to any pair here as is room in K. And the category being proto-modular, since here you are here above the whole rectangle is a pullback, this is of course a pullback. And since GP is proto-modular, you are here a pullback. So you have now a discrete vibration between these two internal groupoids. Now, given any abstract kernel, you can pull back along psi this groupoid, and of course, this gives you a groupoid in the size category above Y. Since the pullback functor preserves finite limits and regular epimorphism, it preserves the direction, and the direction of this groupoid is thus easily accessible once you have psi. It is nothing but the action given by the composite, and the abstract and the direction of this groupoid in the size category Y is nothing but the abelian group above Y given by this formula. If we come back to an exact sequence, you can now factorize the vibration theta of before through this internal groupoid above Y. And since above you have pullback and here you have pullback, because this was the vibration, so you get here an internal vibration. And the benefit of this construction is that now all this part of the diagram lies above Y, so that you have an object in the category, in the size category of groups above Y. And not only, and this is a vibration, so I show now that this group, this object is a deep sea torsor, when the definition of torsor is easily extend from group to groupoids. Given any aspherical groupoid Z, Z torsor is nothing but an object X with global support with the simply transitive action of the groupoid on X, or equivalently with a discrete vibration relating the indiscrete groupoid to the associated to X to the groupoid in question. And conversely, any torsor in the previous sense give rise to an exact sequence with abstract kernel phi. So the main theorem is that the extension between y and k with coefficient psi with the abstract kernel phi is nothing but the set of torsor above the groupoid deep C in J above Y. Now, you have a very general result about abstract Z torsor. The map which define the torsor are necessarily regular epimorphisms, and above all, if you have Z torsor here, namely a discrete vibration, if you complete this diagram by the kernel equivalence relation, this produce here an equivalence relation, and the main result is that there is a unique map from R K0 to the direction of Z, which make this diagram a profunctor between the groupoid associated with this group and this groupoid. And then now we have the fact that the set of torsor above Z is nothing but the set of affine profunctor between Z and its direction. In particular, if you apply this formula to a groupoid coming from an abelian group, you have a set bijection between torsor on A and the endo profunctor on KA1. And of course, we know that there are two structures of groups, the classical structure of group of abelian torsor, and now here you have the composition of affine profunctor. And it is not difficult to see that the two group law coincide, and that the affine profunctor, the group of affine profunctor on this groupoid is abelian, which was not expected a priori. And so the theorem is that when Z, in any exact category, when Z is an aspherical affine groupoid, there is a simply transitive. So the conclusion of this isomorphism is that given any aspherical affine groupoid, there is a simply transitive action of the abelian group of torsor above the direction, related to the direction, to the set of torsor above Z. And the proof, of course, is absolutely now transparent, because when you have two torsor here, since they are invertible to a fine profunctor, since they are invertible, any pair determine here an endomorphism. So the action is absolutely transparent. Now, coming back to the exact sequence, we see that the extension between Y and K associated to the kernel, abstract kernel phi is nothing but the affine profunctor between the direction and the deep psi. Of course, the extension between Y and the abelian group given by a center of K is nothing but the profunctor here in the category above Y. And in this way, we recover the well-known Eilenberg-MacLane result, following which, given any extension with abstract kernel phi, there is an action of this abelian group on this set. But this time, the reason of this action is categorically very transparent, since the extension with abstract kernel pair are affine profunctor here, and they are invertible, and so there is the action of this group of extension. So I hope that the process described in this talk convinced you of how much using profunctor in a place where they were absolutely not expected illustrates the remarkable power of synthesis hidden behind this notion. Well, I shall finish now. I have finished now.
Any questions? Après, c'est David Robert, c'est ça?
Il n'y a pas d'espace pour les questions.
Si. Ah, vas-y.
Non, moi, c'était ma question.
It seems that George would like to ask a question.
Okay.
Not ask my million questions.
Could you speak a bit louder, George?
Oh, is it louder now?
Well, yes, that's better.
Okay, I will not ask my million questions. I will try to reduce it a bit. First of all, I do remember our agreement to do something about this together, and we postponed, but I'm sure one day we will do it. At least I am very excited. This is very, very beautiful.
I hope so. I hope so.
But you know my tradition to criticize you.
Yes, I know it very well.
Yes, and so one thing is that did you try to connect this story of torsors with the story from our joint papers, extensions are torsors?
Sorry?
We had a paper about extensions and torsors.
Yes.
But that was simple abelian case still.
Yes.
Okay. No, that was not critical, but the critical is two things.
Yes.
First of all, your profunctors go to abelian groups, right? Not to sets.
No, there are internal profunctor in the category of groups. In the category of groups.
Mm-hmm.
No, they are not in sets. They are not related in sets. They are internal profunctor.
Okay.
In the slice category of group above Y. So it's why the work of translation between exact sequence and profunctor is a bit long, because this profunctor lies in the slice category of group above Y.
Yes. Okay. That makes more complicated what I wanted to say. At the beginning, you mentioned Bénabou introducing profunctors.
Yes.
Of course, also Ioneda is to be mentioned in 1960. he did require them to go to abelian groups, but the theory is the same. He didn't call them profunctors, he called them A-B groups, where A and B are categories, and it's a profunctor from A to B. And there was this connection with Spence and the xn tensor xm is xn plus m, where tensor is what you were talking about. So yeah, I think Ioneda is to be mentioned. And one more thing, when you write x phi in the top and the index 1 on the bottom, why not using the classical notation MacLean? It is op x, op states for operators, and 1 is always on the top, not on the bottom, because it indicates that it is right derived functor of something.
Yes, because I prefer now I think the problem in terms of torsor, uniquely in terms of torsor, and I try to homogenize the notation. By the way, your question makes me think that in this talk, I give a very, very particular description in the category of group of a process which can be generalized in any category, protomodular category, which is action representable in the sense of Borseux, Janelise, Kelly. And so of the same result I described still hold in the category of Lie algebra, for instance. And then afterwards, it was a work from me in 2008. And then 4 years later, with my PhD student, Andrea Montoli, I exactly produce the same process in the context of action accessible category, which you and me introduced. And so I voluntarily limited my description to the category of group, but behind this description, there are many other power results. But I thought that I was more easily understandable by limiting me to give the description in the category of groups.
Yes. Thank you very much.